Hello everyone. Welcome back to our physics adventure. Let's begin with a simple but powerful question. How do we actually know how hot or cold something is? You touch a cup of coffee and say it's hot. You touch a soda can and say it's cold. But tell me honestly, can you really trust your hand as a thermometer? Nope. Our sense of touch lies all the time. What feels cold to you might feel fine to someone else. So, physicists invented a smarter way, a thermometer, a device that measures temperature using a thermometric property, which means any physical property that changes with temperature. Think about it, the length of a metal rod, the volume of a liquid, the resistance of a wire, or even the voltage of a battery, all these properties change with temperature. The trick is to choose one that changes uniformly and predictably. That's why the liquid-in-glass thermometer became so popular. Mercury and alcohol expand in a nearly straight-line fashion as temperature increases, making them reliable liquid rulers of heat. As you'll see in the diagram, that little silvery thread of mercury inside the glass isn't just pretty, it's a precise thermal storyteller. Now that we have a thermometer, we need to give meaning to its readings. Imagine building a ruler without knowing what a centimeter is. That's like having a thermometer without a scale. To solve this, physicists chose two fixed reference points that are the same everywhere on Earth, the temperature where pure water freezes and the temperature where it boils, both under standard atmospheric pressure. On the Celsius scale, these are marked as 0 degrees Celsius and 100 degrees Celsius. On the Fahrenheit scale, the same points are labeled as 32 degree Fahrenheit and 212 degree Fahrenheit. Between these two benchmarks, the Celsius scale is divided into 100 equal intervals, while Fahrenheit is divided into 180 intervals. That's why the same boiling water can read 100 degrees on one thermometer and 212 on another. Both are correct, just using different units of thermal language. As you'll see in the figure, this calibration process is like setting the two ends of a seesaw. Once fixed, everything in between falls into perfect proportion. Alright, so now you might ask, how do Celsius and Fahrenheit talk to each other? Let's connect them mathematically. The two scales have different 0 points and different step sizes. One has 100 divisions, the other has 180. So, if we take any temperature, we can relate them using this simple equation, open bracket T sub F minus 32 close bracket divided by 180 equals T sub C divided by 100. That's the formula that bridges both worlds. Simplify it, and we get T sub F equals 9 by 5 into T sub C plus 32, and conversely, T sub C equals 5 by 9 into open bracket T sub F minus 32 close bracket. So when the Celsius scale says 0, Fahrenheit says 32, and when Celsius says 100, Fahrenheit proudly declares 212. If you plot these values on a graph, as shown in figure 10.1 from your NCERT, you'll see a neat straight line showing the perfect linear relationship between the two scales. In short, Celsius and Fahrenheit are just two accents of the same thermal language, one metric, one imperial. Here's a fun mystery. Ever noticed that two thermometers might not agree exactly at intermediate temperatures, even if both are correct at freezing and boiling points? That's because they're made with different thermometric materials. Mercury, alcohol, or even platinum all expand differently with temperature. So, their readings may vary slightly between the fixed points. That's why physicists needed a thermometer that could behave consistently, no matter which substance was used. Enter the constant volume gas thermometer, the gold standard for accuracy. It works on the principle that at constant volume, the pressure of a gas is directly proportional to its temperature. In short, P is proportional to T. This means that whether we use hydrogen, oxygen, or helium, the pressure-temperature curve for each gas, when extended, meets at the same point on the temperature axis. That point corresponds to absolute zero, where theoretically molecular motion stops. So, the gas thermometer doesn't just measure temperature, it anchors the very foundation of the Kelvin scale. As the diagram shows, when the gas pressure drops linearly with temperature, extrapolating it gives us the ultimate cold limit, minus 273.15 degrees Celsius. Let's put our equation to the test. Here's the problem: convert 77 degree Fahrenheit to degrees Celsius. We'll use our formula T sub C equals 5 by 9 into open bracket T sub F minus 32 close bracket. Substituting the values, we get T sub C equals 5 by 9 into open bracket 77 minus 32 close bracket. That's 5 by 9 into 45, which equals 25. So, 77 degree Fahrenheit equals 25 degrees Celsius, which, by the way, is the average room temperature in India. So next time the weather app says it's 77 outside, you can smugly say, just 25 degrees, perfect. Alright, let's tie it all together before the bell rings. Temperature measurement begins with a thermometric property, a measurable feature that changes uniformly with heat. We calibrate it using fixed points, the freezing and boiling points of water, to build a reliable scale. The Celsius and Fahrenheit scales are two such systems connected linearly by a simple ratio of 9:5. And when accuracy matters most, physicists trust the gas thermometer, which paved the way to our modern Kelvin scale, where absolute zero means no molecular motion at all. So, the next time you hold a thermometer, remember, it's not just a glass tube with silver inside, it's a bridge between human sensation and molecular motion. Temperature is not just about hot and cold, it's the language of energy itself. I hope this session warmed your understanding, pun totally intended. See you in the next one, where we'll explore how materials expand and contract when heated. Until then, stay curious, stay cool, and keep measuring your world with physics.